Last time we were talking about random variables, and as I told you, random variable, if you can have an experiment, if you have an experiment, random experiment who can have several outcomes, you may be interested in a particular number, or you may assign a particular number that represents a particular event. And then you may query on those numbers whether this number has this particular value or this number is smaller than that or that and so on. It's mostly very feasible. Yeah. It's mostly very feasible if you have associated numbers with events and then query on numbers, because processing those numbers and getting analysis out of those is very handy. You can do it automatically and so on. We gave a lot of examples. For example, let's take another example today. That let's say you have a dice, and let's say this is four-sided dice. Let's say you have a four-sided dice, and you roll the dice twice, or let's say you have two dice and you roll them simultaneously. Okay? Then what's the sample space? Obviously, we can write the sample space as being set of all possible outcomes. And then we have 2, 1, and so on. Finally, 4, 3, and 4, 4. This is the sample space. Now, you may have several events of interest. For example, you may have an event A, which is, let's say, 1, 1, 1, 3, 2, 1. Let's say this one. Let's say this is an event of interest. If any outcome from this occurs, you win. If A occurs, you win, which means either this occur, or that occur, that happen. You may have associated a number with different events or different outcomes. For example, X represents minimum of the two. So for example, whatever your outcome is, X represents the minimum. In this case, the value of X is 1. In this case, the value of X is 1. In this case, the value of X is 3. It's the minimum. Okay? And now you can question, for example, what's the probability that X is equal to 1? Well, that's the probability of event in which all the outcomes are present with minimum 1. So 1, 1, 1, 2, 1, 3, 1, 4, then 2, 1, 3, 1, and 4, 1, all of them. Okay? So once you have associated a number with an outcome, then different values of these numbers represent different events. These are, first of all, these are variables. They do not have fixed values. Second, they are random. If you do the experiment again once more, if you do this experiment once again, then what will be the value of X? Can you say this for sure before the experiment? You cannot. So it's random. So it's a random variable. Make sense? Yes, sir. And we can have, for example, distributions over these variables. Now, regardless of what was the experiment, regardless of how we defined a random variable, we may just start with, given a random variable and its values and probabilities, what can we do further? For example, let's say we have a probability distribution. X is our random variable, and that's our distribution. The probability that X takes the value 6, that probability is 0.3. The probability that X takes the value 2, that probability is 0.4. And let's say the probability that X takes the value -1, let's say this is 0.1. And then probability that X takes the value 0 Let's say this probability is 0.2. Obviously, there was some experiment. X is equal to 6 represents an event. X is equal to 2 represents an event. X is equal to -1 represents an event. X is equal to 0 represents an event. And these are the probabilities of those events. Make sense?
Yes.
But can we, given this, can we start from there on? For example, what if we say, what is the probability that X is less or equal to 4? What is the probability of this? Well, this says a probability that X is equal to 0 plus probability that X is equal to -1 plus probability that X is equal to 2. And you can just add them up. The reason we are adding X is equal to 0, X is equal to -1 and X is equal to 2, why we are not subtracting intersection of these? Well, different values of random variables, they define events that are completely disjoint. X is the event corresponding to X is equal to 6, that event has no intersection with the event that is defined by X is equal to 2. Those two events are disjoint. Because the events are disjoint, probability of the union is just the sum of the individual probability. You need not to subtract any intersection. Make sense? Okay. Let's implement this function. Let's write a code that implements this function. Whenever we want, what's the probability of X is equal to something, it computes the probability from this. Okay? Yes? Rather, what we do really is, let's generate the data, let's generate these random variables. Let's write a function which generates a lot of numbers, and when we count the total numbers, we will see the total number of zeros are only 20%, total number of -1s are just 10%, total number of 2s are 40%. Let's write such a number. Let's write such a function which actually respects this distribution. Okay? Let's do it. I don't know where I have. Okay. I guess this is visible? Yes? Okay. Let's write a function, generate random number, and this generate random number receives the possible random numbers list. What is the list of random values? I mean, those are, if you remember, 6, 2, -1, and 0. Whatever sequence you give, then you give their respective probabilities, and we will generate and then probabilities of that. Okay. When we will call return, it has to return a number. Let's say it has to return a number y. Okay. Let's fill up. This is the implementation. We will do this implementation later. Let's see what the caller look like. X list is 6, 2, -1, 0. 6, 2, -1, 0. We can convert it into array for faster processing, although list is just as fine, but it's good to come up with array. Then P is the probability distribution. That was 0.4, I guess. 0.3, 4, 0.4, 0.1 and 0.2. 0.1 and 0.2. And then y, which is our random number, looks like the following. Okay, so that's how we will call it. Obviously right now y is none, so if we print y, we'll get nothing because, but that's. So let's now start writing implementation of this function y. Okay, if let's generate a random number r, np.random.rand, let's generate it. It's just a number. If that r how can we write this function that if this is in this percent, then so let's see, if r is less than p, loop लगा लेते हैं, let's have a loop for I in range if r is less than p I, that's for 0, that means return x list I. अब क्या करें, elif any idea? No? Let's have a fix. Let's start with p so far, what we have covered so far. If that is p so far plus can anybody tell me what happened here? So what will that bring up? For example, let's say we generated this random number and the random number just appears to be, let's say the random number, let's see here, let's say the random number is just, let's say 0.7. Let's say that's the random number that is being generated. What will happen? Sorry? Right now what code we have written is, if it is, so let's run it. For example, for the very first time, p so far will be 0 and r is less than pi, which is pi is 0.3, so it is not less than that. Next time, p so far will contain 0.3 and the next probability will become 0.4, and it says okay, now the probability becomes p so far plus pi, that becomes 0.7. Okay, and let's say we have written here equals to, let's say. Then it will return, for example, x is equal to 2. Should it return x is equal to 2? Yes? Hmm? Probability is 0.7? No, if the probability is 0.4, only then we have to return 2. Now we are returning 2 when this random number is actually representing the probability. When it is 0.7, it is returning 2. However, it should have returned 2 when the random number was 0.4. What should we do? Sorry? What check? I mean, can you help? We want to do this. If the random number is, if the random number what we have generated, if it is till 0.1, then we have to return -1. If the random number is between 0.1 and 0.3, that means 20%. Okay? If it is between 0.1 and 0.3, then we have to return 0. If it is between 0.3 and 0.6, then we have to return 6. Otherwise, we have to return 2. How can we write that logic? Did you get the point? Yes? So how to write that logic? Can you help me? Sorry? But right now these are just 3 checks. You can go and write the checks manually. What if this distribution goes for 50 variables, 50 values? Will you write the 50 checks yourself? Write the checks in loop. Yeah, how to write that check here? First of all, I guess we should sort the probabilities in ascending order and their corresponding numbers in ascending order. Yes? Let's do that. So that we know this is smaller one, then this one, then this one, and so on. Let's do that first. P sorted, np dot sort P. Actually, we want org sort. What this org sort does, I will just show you right now. P sorted. This is no longer list, it's NP array. What it does is, this actually give us the indices, the indices that should be shuffled in this particular way, and the array will become sorted. We pick those indices and we apply those indices to P. P is sorted. If we apply the same indices to X, X is accordingly shuffled. Accordingly shuffled. X is not sorted, it's accordingly shuffled. Make sense? Now we have the minimum value in P, then the next value, then the next value, then the next value, and so on. Okay, now this is our random number, this is some number. How can we go for this? If it is between, if it is less than pi, if it is this one, then we do this. If it is between if this R is less or equal to 0.1, then we have to return -1. If it is, yeah, but I want the code with respect to this. So I want to do the indices, or I just want to stay in the terms of I and stuff. But how? How come? The first check is very good. The first check is just okay. If it is smaller than 0.1, return the corresponding, which is -1. Now we have to show if it is greater than 0.1, and less than 0.3, which is the 20% total. How can we write that check?
लिस्ट में तो ith एलिमेंट पे चेक लगा और जो लिस्ट है उसके ith एलिमेंट जो है उस पे चेक लगा
Yeah, can we do that if it is less than that and R is greater than P so far? Will that help? If R is greater than that and less than that, then will that help? See the code. Will that help? So let's dry run. Let's say we again have 0.7. Okay, 0.7. And let's say what should have been returned. Let's see. But 0.7 तो किसी की भी probability नहीं है.
0.3 और 0.7 0.7 तो P so far तो minus 0.3 भी तो करना है.
Let's see. Let's say R is 0.7. Let's say. If R is 0.7, what should have been returned here from here? Nothing. R represents a uniform probability. A uniform probability. If it is between 0 to 0.1, then it should be minus 1. Sorry? So left limit and right limit. So 40% is the probability of 2. 30% is the probability of 6. 1% is the probability of minus 1. 2% is the probability of 0. If 70%, a number 70% is generated, nothing should be returned. Yes? But how can, I'm confused. How to generate these numbers? Sorry?
Dice की कोई ना कोई side तो आएगी ना.
Which dice? Right now we have no dice. This is some experiment. Based on those experiments, we have these values available. And we have these probabilities. All we want is to generate random numbers, a lot of random numbers, such that when we count them, we see that zeros, total zeros, are 20% out of total. Total minus ones are just 10% and so on. But I'm confused how to write the code for it.
Something like probability of 70%. Maybe the combination of multiple probabilities in numbers and with a combination of some events.
But these are the total event we are interested in. X is equal to 6, X is equal to 2, X is equal to minus 1, X is equal to 0.
Maybe 6 and 2 happens together, so they might be 0.7 and it may be an event.
When you do an experiment, only one and exactly one value of random variable will you observe. Because one of the events has to fire on exactly one.
We have just to terminate this thing whenever 0.
When we do,
maybe 0.
I don't know, that's what I'm asking you to help me because I'm lost. How can we generate the numbers that respect this distribution? By the way, this is called random sampling. Given a distribution, generate numbers or draw numbers from that distribution. This is called sampling. How to do random sampling. And in general, if I give you any probability distribution and I ask you to generate numbers that respect this distribution, how will you go and write the code for it? It's very easy, by the way, generating random numbers like this, having only two values of random variables. For example, let's say I have a random variable y, and I have just two values, 0.7, or is x is equal to 5, 0.3, x is equal to 7. Very easy. I will generate r. If it is smaller than or equal to 0.7, return 5, otherwise return 7. But once the values go beyond three values, for example, x is equal to minus 1, and let's say this is 4, this is 3, and this is 3, how will you go and generate the values? Get the point? How will you write if conditions in a way that, sorry, yeah, sorry,
टर्मिनेट हो जाए प्रोग्राम की ऐसी चीज इनवैलिड है कि ये हो जाए कि कोई नंबर फिर भी वो शो
सर
करे।
हम ऐसे भी तो कर सकते हैं कि ये हमारा बोर्ड ऑफ ट्रस्ट में ये नंबर नहीं है हमारे पास, ये सैंपल स्पेस में हमारे पास नहीं है।
see, this is the distribution, like just like this one. Probability of y 0.8 if y is equal to 3, 0.2 if y is equal to, let's say, 9. We can very easily write code for it. Yes, there is single if condition on R. If R is less or equal to 0.8, return 3, or whatever that number is there in the array. Otherwise, return this. What if I add another number, y is equal to -1, and the probability of that is 0.3, the original, this probability is 0.5. How we will go now? Yes, with what check? Yeah, what check?
0.2 से कम होगा तो हम 9 लिखेंगे, 0.2 से ज़्यादा 0.3 से कम होगा तो -1 लिखेंगे, और उससे ज़्यादा 5 से कम 0.5 से कम होगा तो 3 है। 3 चेक्स हो जाएंगे।
So if it is smaller than 0.5, if it is smaller than 0.5 and greater than 0.3, so this and doesn't this help here? Is it the same thing?
Yes, sir.
If it is greater than 0.3 and less than 0.5, it is only 20% now. If it is greater than 0.3, if you are writing a check, it should be greater than 0.3 and less than 0.5. You are only focusing 20%. No, you should have focused 50%. You should have focused 50%. So the check should be if it is greater than 0.3 and less than 0.8. That should be the check.
Top 3 आ जाए, top 3 आ जाए।
Now you have 50% bucket. See, if let's say R is generated, some number R is generated. If R is less than 0.2, return 9. Yes? If R is greater than 0.2 and less than 0.5, now you have 30% cushion available. Now you return -1. Okay? Otherwise, you return this.
Yes, sir.
So what I'm asking is this code fine? Yeah.
कहते हैं 0.1 से लेस है तो 0.2 9 कैसे रिटर्न हो?
If it is
लेस देन 0.2 है ना?
no greater than 0.2, if R is greater than 0.2 and less than 0.5, this one?
यस
पहला check।
ये तो फॉल्स हो जाएगा ना?
Oh, if it is less or equal to 0.2, that means only 20% chance is there. On the number line, you have a line of from 0 to 1. You are covering this portion. If it's
less than भी तो नहीं कर सकते।
less or equal to, if it is
0.2 होगा तो 9 देगा।
no. If it is 20%, so this is the cushion of 20%. Everything falls in that bucket. Listen, we have 3 buckets. Let's say a 2% less than 2,
Then we have put another check.
from 2 to 5, okay, and then the rest. Falling in this has 20% chance. Falling in this has 30% chance. Yes? Make sense? That's what we want to do. Now, does this code make sense? Is this okay? Is this code right? P so far is containing a where we are now. Yeah. Let's try and generate a few numbers. I guess there is a bug in it, and then we will find out that bug. Okay? Let's first try to generate, let's say, 1,000 numbers and see what portions of those numbers they appear actually. Okay? Let's do it. I have to. Okay? Now we are generating a lot of numbers, we are just appending them in a list. So y, we have y now. Let's see how many of those y's are exactly zeros. Okay, so oh, none of them. None of them is. Oh, y contains none. Why is that happening? So it's not coming in this loop. Only integer scalars can be converted to scalar index. IDX. Two 984 out of total. So let's see what is X list. 0. That is 6. So total number of 6s are 2984 out of 10,000, which is 30%. Yes? Seems like, yeah. Seems like yes. Let's see. Let's see for other numbers. Let's say X list 1. So print that. Actually print this. Divided by length of y. And then print P of 1. अभी खत्म हो जाएगी बेटो. You see, it's 40%, 40%. Yes? Let's check for all of them. Get the idea? if we generate more numbers, for example, maybe it become very close, as you can see. If we generate even more, make sense? Get the idea? This is called random sampling. Given a distribution, that's called the distribution. Okay? So if, here, can you ask them to slow down? Okay, get the idea? Okay. Just one more thing. See. We have generated a lot of numbers. Several of them are 6, several of them are 2, several of them are -1, several of them are zeros. Let's take the average of all these numbers. Let's just take the average. What happens? ठहरो भी चलते हैं, बैठो। ये इंशाल्लाह आइंदा नहीं आएंगे, इनको काफ़ी थी कि हमने क्लास लेनी है, नाउ दे आर आस्किंग कब ख़त्म होगी, समथिंग लाइक। या आई कैन अंडरस्टैंड। सी वन मोर थिंग, द फोकस, so the average value, just give me 5 minutes and then the next 20 minutes. So just 5 minutes. क्या आदतें खराब हो गई आपकी?
ये घड़ी पीछे है, 5 मिनट ज़्यादा चल रहा है, एक पूरा
बिल्कुल सही है।
ये एक बार ये 4 मिनट पीछे।
Okay, let me close this concept and then बैठो मैं आप फोकस नहीं करेंगे, मैंने ये करा के जाना, आपको जल्दी फोकस कर लें, जल्दी खत्म हो जाएगा। चुप करोगे तो पढ़ावांगा। Okay, focus. I have generated around a million numbers from this distribution. Then I took the average of those million numbers and it just appears 2.50 and something. Yes? Now just do one thing for me here. Just multiply this quantity with this number, multiply this quantity with this number, multiply this quantity with this number, and multiply this quantity with this number, and then just add them up. See what happens. Have you done it? Show me.
0.18 होगा ऊपर वाला, उसके बाद 0.2 और होगा, 0.20 हो जाएगा।
एक मिनट, 0.18, 0.18 है या 1. I guess this is 1.8. What is this?
0.8 सही किया।
Is that 2.5? Is that magic? These are a million numbers we processed. A million numbers.
In just 1 second.
And we just take their average. And that average is exactly, just multiply these numbers together. Can anybody tell me what happened? Okay, tell me, otherwise we are. Okay, I am leaving this question as a homework. Listen, listen, listen. Let me tell you, this concept has a name, and this is called expected value. So you have to go home, you have to understand why this happened. If we have a distribution, we generate a lot of numbers respecting those distribution. Their average just becomes this particular number. Multiply probability with a number, then next probability with next number, and so on. Just add them up, we'll get exactly the same number. What is that? Yeah. It may not be that simple, but maybe this simple. You have a day, for example, tomorrow, you can just figure that. No book. Just go internet and understand. I've told you expected value. By the way, I've given you the book, soft copy on the group. But that's not easy to go through, but that's a good book. No outline. Just, yeah. Okay, on Wednesday, we will be having quiz from this concept, which is called expected value. Okay? Expected value of a random variable. Clear? Okay. बहुत शुक्रिया.